looking at insecticide treated nets with the Malaria Atlas project. Yeah, so we're interested to see what he's been up to since submitting his PhD.
Yes.
I'll let you take it away.
Thanks. It's nice to be back, I guess. I haven't been away for very long. So, a bit of context. This work is kind of basically done under the Malaria Atlas project, which was based in what was formerly known as the Telethon Kids Institute just across the road, which is now called the Kids Research Institute, but all the kids. And I thought, so Braden asked me whether I had anything to present. I thought maybe work on a bit something more application focused, so that it's not going to have a lot of mathematical rigor per se, but just a few insights on using various mathematical and statistical and machine learning-y type ideas for a data analysis problem. And the title here is something to do with insecticide nets and failure behavior, and I'll go into that shortly. So just in case y'all don't know much about malaria, I'm also kind of new to this thing about malaria. But essentially, that disease in Africa has a really complicated epidemiological spread dynamic, and has also very interesting things such that the parasite actually lays dormant in the person, and eventually the person gets sick after several weeks and then becomes a source of spreading to another mosquito. So it has a very complicated kind of spread cycle, but the main part to think about this is that one of the main vectors is a mosquito. Okay, that's all you're going to have to take out of it. Now, what drove this research is that in about 2000s, there was a concerted effort to try and figure out a way to tackle the effects or combat the effects of malaria deaths within Africa. And they tried various things. Now, there are three main categories of interventions that you can that exist right now. So there's IRS, which is essentially spraying residential areas with insecticide to kill the mosquitoes. There's ACT, which is basically a drug, artisan drug therapy, which I believe can be done as treatment, but I think in some cases there are also prophylactic versions of it. But by far and away, the predominant intervention treatment that has the biggest effect in terms of protecting people from malaria from mosquitoes, which would then result in malaria infections, is what we call ITNs, insecticide-treated nets. This is a figure from a study that was done in 2015, which later you'll find out is actually a predecessor study to the model I'm working on now, which kind of tries to ask, well, we have these interventions in now, and this is how many deaths we had. What happens if we never had them as a counterfactual? And what we see in the last, from 2000 to 2015, we see a very large decrease in, first of all, the incidence or the estimated incidence of this parasite within the population, the parasite that causes malaria. And a large proportion of this has been due to the fact that nets have been given to populations to use, and they're responsible for the large decrease in these deaths as well as the infections.
So everything but the red line is model?
Yes.
Model.
Model of the estimated effect that these could have done. Now, why this is interesting is basically from 2015 onwards, well, first of all, why nets? Nets are relatively cheap compared to administering drugs. That's the main reason why. It's easy to implement, easy to give to the population, and it's kind of a very direct way of targeting malaria. The thing is, what you don't see after this graph is from 2015 onwards, there has been a really large slowdown in the decrease of deaths in malaria, and in some countries, this actually has increased. Combat with that is that the insecticides that are used for the nets have now caused some of the mosquitoes to be drug resistant, right? So it's this complicated phenomenon. But in the simplest terms, we want to kind of figure out how many nets are there in a given population, which is quite hard to figure out given the large size of these countries. You don't know what the use cases are. You want to figure out also not just the amount of nets, but also how old are the nets, what is the status of the nets, and why you want to know this is so that you can figure out, are these nets really efficacious for their task? So do they actually do what they intend to do, and what is the type of net coverage within the population, which will then hopefully be used downstream for policy, right? If you know a certain country tends to use nets really effectively, you might put more nets in there in terms of value for dollar than compared to another country. So ultimately, all this, while it starts off as an accounting exercise, should hopefully shed light on the behavior of nets, which would then subsequently be used to inform policy for some kind of vague optimization problem at the end.
What's a net?
Oh, it's a bed net. Like it's a net that someone sleeps under.
Oh, under a bed.
Yeah.
So you give a net to a single. You're not putting Africa.
No. So essentially, the nets get distributed by governments in various different programs, and they're literally just a net where ideally 1 or 2 people sleep under to protect them from mosquito bites at night, where mosquitoes are more active usually.
And the net is laced with this drug.
Yes. For ITNs, they're laced with a specific type of insecticide. Yeah. Whereas ACT are literally like an administered drug for treatment, which is a different type of intervention.
Drug given to the
Person. Yeah.
Is it?
They won't swallow when you give them the pill.
I've seen the biologists do all sorts of things.
So the nets stop working because they've worn out and they've got holes in them?
Depends on the net. So later on I'll talk about, there's 2 main types of nets, 2 main mechanisms. The first one is what we call conventional ITNs, which kind of existed in the population pre-2009 in large proportions. And essentially these are like woven nets which have been dipped in insecticide, dried, and then installed in the house. And you can kind of tell that that's going to wear off, and also every time you wash the net, you lose all the insecticide. So from 2010 onwards, or about around 2010, basically there was a shift to move to what we call long-lasting insecticide nets, where you could wash them. The insecticide just stays there. And so that's the other one. Obviously, there are also issues, because you want to find out some people use these nets not for sleeping under, because it turns out nets can be useful for a lot of other things, like catching fish. So we want to figure out these inefficiencies, or try to vaguely model these inefficiencies to drive policy. Does that answer the question? Yes. So, and this is where a little bit of history kind of plays a part. So I mentioned those figures from the BART paper in 2015, which was what was basically the first attempt-ish at trying to tackle this problem of how many nets are there in the country, because you've got people pumping in nets into this country. They don't know what the effects are, and they don't know how many nets there are, apart from very, very vague surveys. Well, not vague, but very sparse surveys. So what it started off with is the first 2 boxes, where BART in 2015 did that study to try and figure out the number of nets. And in the simplest way possible, it's very much a compartmental accounting exercise, because nets flow into a country, nets disappear for whatever reason, and also nets flow out of the country or get used up. So, and I'll go into more detail of what that stock and flow actually looks like, but for now, think about it as it's a compartmental model where there's an inventory tracking of how many nets there are. Now, after you do that, you can also calculate the next metric, which is net access. Does any given person typically have access to a net? And the definition we will use here is the idea of having access is that you have 1 net shared between 2 people, right? That means you have access. If you have access to a net that's shared with at maximum only 1 other person, you are determined to have access. So you want to figure out what proportion of the population have access. That was in BART in 2015, and then this was then improved upon in 2021. Some mechanistic stuff was added and simplified here, but they've furthered it by looking at defining more metrics on this, and specifically you have these surveys or information on national levels, but you also have information on things like forest coverage, rainfall, all that kind of thing, which you can perhaps use to try and as a predictor for this excess that you've calculated. Because the hypothesis is that having knowledge of what the typical shrubland is, or the aridity or the rainfall or various covariates could inform or predict roughly what the excess is like in a specific region. And so basically the aim for that was to go from a national metric, which was national net excess, and trying to disaggregate that into a more local, like within this village or within this 5 by 5 kilometer square, net excess is a certain amount. So, and the thing they were interested in is basically the gap between a given location access and the national access, because they would tell you what locations is purported to have inefficient use of nets or insufficient nets, and then you would target programs in those regions. So that's the state of the art kind of up to 2021, and the work here is essentially a continuation of that and hopefully an improvement to tackle what is essentially more the types of data that's coming in now from these countries being firstly of a different form. The situations are also different, but also we have slightly higher resolution data coming in the future. So preparing the infrastructure for that. So I mentioned there's a stock and flow model. This, most of this has largely stayed quite similar to the, what I call the Bertozzi-Villa, but I'll call it BV for now. The BV model. And essentially, because all this analysis was done on data where we didn't have very accurate data, but we had data from a lot of different sources. So the one thing I want to keep to highlight is essentially there are 3 main data sources that we need to reconcile in this model, or that this model tries to reconcile. First one, we have information on how many nets a given manufacturer has delivered to a country's government. And this is source data, so basically they had to go and ask the manufacturers themselves. So we have a tally of how many nets have purportedly been given to the government or to the country itself, and which means the country has a running stock of an inventory of how many nets they have. Now, on top of that, the governments may also have campaigns where they actually take these nets and distribute them to the public. Now, these campaigns come in many different forms. Oftentimes, it's a mass campaign where a bunch of nets literally gets dumped into the public at some point in time. But there are also kind of trickling consistent campaigns where, for example, they give it to pregnant mothers or new mothers, because infants and pregnant mothers are actually have special vulnerabilities to malaria. So we have information about deliveries going to the country. We have information about distributors or the government actually distributing these nets. Now you can imagine some of these nets will get lost along the way between delivering to a government and then the government distributing it out. But we have these 2 information. Now on top of that, what we do is the governments actually do national surveys occasionally, and when I mean occasionally, it could be anywhere between 1 every 3 years to once every 20 years, right? Depends on the country. And these national surveys basically consist of people going, officers going from household to household in a bunch of different areas and asking questions like, how many nets per capita, how many nets do you have in your household? What is the size of your household? How many nets do you use or did you sleep under yesterday night? Things like that. Which means these nets give a very rough picture of what the number of nets are roughly per capita in a given region. And the stock and flow essentially tries to do a few things. Firstly, it tries to reconcile differences between what is supposedly delivered to the country and what gets distributed, which is this part here. For now, essentially phi and beta are just adjustment terms to deal with that evolution to kind of fix the numbers a little bit. But then one aspect is these nets slowly decay and fail, or we won't say fail, but they disappear from the system naturally. Either people throw them out or gets used for fishing, right? We don't know. And so there is a model that needs to be learned here, which is that characterizes net failure, or more specifically net attrition, at least in terms of their presence in a country. And the idea is to match these 2 to what is the purportedly observed net crop, which we are going to assume is relatively representative of that real net crop. And why we want to do this is because these surveys are very punctuated and sparse in time. You may only, in a 20-year period, you may have only 3 or 4 surveys, but what you want to do is figure out what a net crop is at any point in that 20-year period, or infirm, right? So in the simplest way, it is kind of like line fitting, and that's the main challenge in the line fitting. As I mentioned before, the main difficulty with this problem is that all this information here is very regular. We have data, but it's every year. Now, the surveys are kind of on the monthly resolution because these surveys take time, which means if they report what month the survey was taken, even though a survey takes 4 months to do, it at least gives you some information across net crop for 4 months, but they are also very sparse. So in 20 years, that's about 240 months. You may have 3 surveys, so really you only have 12 kind of points to fit, which becomes a bit of a problem. And they're not regular either, they're very irregularly sampled. Now, the first part to tackle here is essentially what are your different net failure models. When the model, when the MAP or the insecticide treated stock and flow model was first proposed, it was coupled with this proposition of let's use this exponential function. Some things, yes, it's sigmoidal, so seems pretty reasonable, and yes, that was my first reaction to when I first saw it. I was like, that's a very, well, that's a choice. And the argument was, we don't expect nets to live forever, so we want to choose a function that has a limited support. It's just a very general sigmoid function with artificially truncated domain. And other arguments, I said, compared to other types of functions, this has a better information criterion score, so we're going to do that. Now, that's where the arguments for it ended. Turns out, if you try to do Markov chain Monte Carlo on that, the fact that one of these terms directly affects the domain is not good, because it's very hard to do random walks when you have a giant singularity somewhere. I mean, even though it doesn't affect the output, because it's infinitely, it just doesn't like it. So, no. So that model kind of got shelved. The successor decided to essentially use a similar model because this was what was standard in studying these nets, and assumed kappa is 20 because it seemed like a reasonable number, and basically said, well, the main factor affecting what we're interested in, which is the half-life, would be tau, which we're going to figure out from the regression problem. Now, there's a slight issue with that. If you do a little bit of algebra, you find out that, in fact, the thing that affects the shape is not actually tau. Tau just affects your dilation. The main thing that affects the shape is actually kappa. So that's a slight issue. And in terms of interpretability, because we would want this model to be as interpretable as possible. So first improvement, let's just use a Weibull. Nice domain, 2-parameter system, relatively flexible. What could go wrong? Turns out a lot of things, but we'll go into that later. Now, so that was more the mechanism that's challenging. The next challenging part was trying to deal with the fact that you have data in 2 different resolutions, one being regular, one being sparse. So this is essentially all I'm given. For now, you can think about it this way. I have annual manufacturer data that is in the year. You have annual government distributions which do not agree with the annual delivery data, even though they should. And national campaign data, which are in like little months, but punctuated very concentrated in small moments in time. And you're trying to fit a curve to all of this. So what the BV model, which was the first innovation on this, was essentially saying, well, what we can do is, if this information is on a monthly basis, we can average it into a point in time, single point, and use that point as a summary of the survey observations. So instead of having like multiple months of observation, average it to a single point in time. And what we're going to do is we're going to disaggregate the annual data into quarters. So you have this thing that belongs to some quarter somewhere, and your annual data is now disaggregated in quarters. And another assumption they've made here is basically it's going to be a uniform distribution. So if I supposedly distribute 1 million nets in a year, I'm going to roughly assume that's like 250,000 nets every quarter. That is good in a sense that it simplifies the problem a little bit, makes everything a bit more regular. And that averaging part here actually is not as unreasonable as it appears if that averaging is a sufficient enough statistic and everything behaves nicely. The argument why you wouldn't want to do that is what you expect typically the half-lives of these nets are about 1.5 to 2.5 years. And if that's your half-life of a net, 4 months can be a long time. They are not too far in time scale, right? So aggregating this to an average may not necessarily work in terms of the relative timescales of these two processes. So that was 2021. What we're proposing to improve on, to change, was basically, well, we're not going to assume that it's uniform. We're going to assume that in any given year, I know, for example, in a given year, I'm allowed 1 million nets to go out into the population, but I don't know what proportion of these nets go out in a given month. And I'm going to treat that as variables that I will need to figure out. Now that poses some problems when we're trying to do sampling, because as you can kind of roughly predict, the number of variables are going to increase by a stupid amount. So let's pause on that for now. But the idea is we're going to try and figure out what is the distribution ratios in a given month. So for example, if I was given 1 million nets to distribute in this period of time, and there's a really big peak here, it's kind of implying that most of these 1 million nets were distributed in May, for example, May and June. So that's assuming if we can figure that out. And why is that important is because, well, as I said, depending on what the distribution campaign of the government is like, oftentimes you will find that these surveys happen quite soon after a large distribution campaign. Now, there are many reasons, good and bad reasons, why you would want to do that. Good because it's also a good opportunity to figure out whether these nets have gone to the population correctly. Inaccurate because it can sometimes bolster the reported coverage of nets, right? So having knowledge of, or having an inferred knowledge of when these nets went in the population is actually a good thing if you can figure it out. Unfortunately, while this data does exist, it exists in literal handwritten sheets of paper somewhere buried in an office or in an archive, and very hard to access. So in the essence of efficient use of time, can we just try and infer this based on the data? Now, if there is data available, we can always condition on that and adjust things, but how do we create a general framework for that for now? But this firstly requires one thing, right? I mentioned these are over several months, and oftentimes we need to figure out first, are these surveys in a given month, are they just concentrated on one area, or are they relatively spread out? Because if they're concentrated in one area, what's going to happen is that your data for 1 month could be skewed to the demographics of one area, and then if you survey another part in another part of the country, the demographics could be really different, and you're going to have really large volatilities in your observed survey estimates of net crop. So we just got to check. Yeah, essentially every color here is a different month for a given survey, and for most cases, Madagascar is example of what is not good, but for everything else, they are relatively spread out-ish, right? So for example, in here, it's a bit hard to see, but the pink/purple is not that concentrated in only one region of the country. It's relatively spread out, so we're going to use the argument and say that even within a given month, these surveys are homogeneously surveying the population-ish. So now that's all well and good, but how does it work with regression? So let's count the number of parameters we have, because we all know MCMC does not work well with large number of parameters. Firstly, you have two parameters that are related to do with the fact that deliveries and distributions don't match up. You need to know the rough initial number of net crop when you first start the inventory, because that's going to have problems if your survey says that there should be nets in the system, but then there are none. So you need to have something to deal with that. If you have one type of net, you have two attrition parameters to regress, because that's your attrition curve for the Weibull. Now, I mentioned if you have one net, actually from 2000 to 2020, you actually have two types of nets, right? You have conventional ITNs, where you do the dippy thing in the insecticides, and also long-lasting nets, of which the dynamics would be different. So you need a factor to convert between these two. So that's 1, 2, 3, 4, 5. And if you have missing data in the distribution, which yes, there is, you've got now however many missing data points, you can impute that missing data point, which basically gets treated like a random variable. That's actually not the bad part. The bad part is the distribution ratios, because what you have now is, if you have 20 years of regression to do, 20 times 12 is 240 parameters. So compared to the model, the model seems like a piece of cake compared to that. So that's a problem. And how we're going to tackle that is essentially I might be using this term incorrectly, but an expectation maximization problem. So if we split those parameters in two groups, so the first group is your actual inventory management parameters, which is basically, you call it calligraphic M, which is your distribution, your initial values, and your attrition. Shove that in one side. And the other stuff is your annual to monthly distribution ratios, which are large in number. Essentially what we're going to do is we're going to start with some assumption of what D is. Let's say it's uniform. Do a regression of a regression of basically these parameters using some MC approach. And we're going to fix those parameters and basically tweak these distribution ratios. And why that's useful is because these ratios actually may not affect, on their own, may not affect the result too much. And they also will affect it relatively predictably. So what we're going to do is this tweaking is going to be done via a gradient descent approach while fixing these parameters constant. And you can imagine these goes back and forth, until you arrive at a combination of stock and flow model parameters and distribution ratios that attempt to best fit the data. And here, the gradient descent is done with respect to some loss function, which in its generality is related to root mean error, but that takes uncertainties into account. And so that's everything in stock and flow. So that's the first box in the wider map ITN model. The second box is actually net access, because these two actually work together. Because it's no point knowing how many nets there are in a population. You also want to figure out whether people have access to nets. And the surveys do have estimates of whether people have or how many people have access. And now we're going to actually use those surveys as a validation exercise, because we know what the definition of access is, right? We define it as one accessible net between two people. We're going to see whether our net crop, alongside with this assumption, is going to reproduce the supposed access that we observe from the survey. The problem now is, how do we convert from net crop to access? Well, the naive way would be do something like this. If it's one accessible net between two people, take the number of nets, divide them by number of population, gamma is the number of nets. And then normalize it. Essentially, you get a number from 0 to 1, which tells you what proportion of the population, in a very naive sense, has access to a net. And if only life was so simple. So the problem is that the number of nets available to a household is actually very dependent on household size. Because if you think about it, if your household is 1 to 2 people, you really only need one net, right? The quantization has an effect. If you increase the household size, the number of nets you require does not scale quite so linearly. There are a few sociological factors that affect that. And also, there's a high chance, if you have a large household size, there is correlation between household size and your relative access to funds and accessibility of these services. So we need to consider it on a household basis first, rather than just taking the number of nets divided by the population. And if you kind of look at all the surveys and see what is the distribution of household size, ignore the line for now. The line will come back and make an appearance later on. Just look at the orange dots. We see that, yes, for households of size 1, so people who stay alone, there is a big variation in distribution. But for the most part, we see a peak at household size 4, and then it decreases. But we're not interested so much in the household size, but how that affects the number of nets you expect to see in those households. So what we're going to do is, the aim of this is to create this matrix up here, H, which is basically the joint discrete distribution between the number of nets and the household size. So what's the probability of observing a household of size h with n number of nets? You want to basically figure out the probability, because then we'll use that to convert for access later on. So you're going to try to work out everything on a household level and then do a bit of arithmetic to get to the population level. So it's it deals with that bias of households. Essentially, if you look at the conditions, so the probability of a household of size h having n nets, given its size h, we're going to model it like a zero truncated Poisson. So in the zero case, it's special, but everything else it's Poisson looking like. Now, turns out it's quite a nice, a nice property, and it's a relatively simple model, except this requires us to fit two parameters. Two parameters which basically govern how the mean number of nets varies with the household size, and also the proportion of households of size h with no nets. So essentially, this is going to be a global model that will be used to convert from net crop to net excess across all countries, but this requires us to fit two parameters, mu h and rho h, which is a different fitting problem to the first one I talked to you about. But once we find those parameters, we can calculate the joint distribution h, which the plan is to then normalize that with the number size of each household, and what you can then get is a different distribution, which is really the proportion of people who belong to a household of size h with number of nets n, rather than the proportion of households, which is then now basically a bias corrected version of the previous one, which you're going to use to calculate net excess. And this is essentially what your national net excess will be, which is still a number from 0 to 1. Well, you have all the survey data, you can basically regress those parameters, but I won't go through into this. Essentially, this is your regression of that rho h parameter, and all it tells you is that if you have more nets, if you have more nets per capita, the proportion of people who have no nets for any given household decreases, and also the bigger your household size, there is this weird non-linear relationship. But the more interesting one here is actually the one on the right, which tells you how many nets do you expect the household of size h to have. So if your household size 1, on average you have 1 to 2 net, 1.5 nets. And this scales relatively linearly. Although what you'll notice is that, for example, here the nets per capita, households of size 1, your nets per capita is about 1.5. Here, you typically have 4 nets for a household of size 10. So if you were to divide this figure by the number of nets, you'll kind of notice a plateau happening, which is exactly the phenomenon we want to capture, because what we see is even though larger households may numerically have more nets, if you divide by the number of nets per person, you see that it actually decreases. So we wanted to capture that. So that's cool. Now, I promised you line fitting, so there is line fitting. Now, there's a lot going on in this graph. So imagine all the stuff I've gone through before, put in practice, put it through the magical machine of computers, and I've taken 4 kind of, I want to say representative, but interesting cases in terms of the types of data we have. So the first one is Benin, which is a country that gets scrutinized very often and seeing whether it makes sense. Now, wherever you see the blue dots, those are the survey estimates of what the net crop is in millions. The red dots are the survey estimates of access. Now, the blue lines are then the result of, once you regress those attrition parameters and you combine that with the delivery and distribution data, is the prediction of how much net crop is at any given month. And the red line is take that net crop, shove it through the excess model, and that's why you get your predicted excess. Then there's uncertainty bounds here. The orange lines was basically that distribution ratio I talked about, where you had to use a gradient descent to figure out, for example here, within the year 2010, right, in order to fit the data, most of the distributions would likely have to have been done at the start of the year, with very few done at the end of the year. In fact, this is quite, it makes quite a lot of sense because a lot of countries do this punctuated mass campaigns at a short period of time, which then decreases. So we're trying to infer this and correct for this data without having much knowledge except the surveys. So the first case, Benin, is kind of a alright, nice-ish case because they have some data pre-2010 when they still had conventional ITNs in the system, and there's data after 2010 where everything started moving to LLINs. Great. And then we have countries which have basically really bad data, like I think that's Mauritania. Now you might be wondering what's happening on before 2010. Because before 2010, there were CITNs, a lot of CITNs in the system, but there are no surveys of the number of CITNs for this period. So, conventional ITNs, the nets that are dipped.
So my question is going to be, there seems to be a lot going on in the pink line and the blue line, and you've got very few dots that you fit into.
Yes,
So
and
you're fitting something else as well.
in this part here,
Or in all of them. If I was to fit a curve through the blue dots, it wouldn't look like those curves.
yes, so the thing is, because it's not just fitting a line, it's fitting a driving input to a system that's evolving, and the output of the system has to match the lines. And yes, I agree there's not enough data points, which was the reason why we wanted to go from 3 surveys equals 3 data points to 3 surveys equals 15-ish data points. And yes, there is a bit of an issue with sparsity of data, and I am quite aware of that. The only redeeming grace is the supposed argument that these surveys are relatively large in sample size, so there is a large confidence in that. Yes, but I understand your point entirely. Now you might wonder, well, Kenya's pretty similar to Benin. In fact, it's a bit of a nicer case than Benin, which is the bottom right. There's more data, but what the hell is going on with Senegal? And you might notice the lines kind of match up-ish, but also the dots are kind of all over the place. So what's going on there is actually Senegal has a very interesting way of taking surveys because they do rolling surveys. They might survey, it's basically, the survey takes a long period. It's kind of like painting the Golden Gate Bridge. You survey a bunch of areas, and eventually by the time you finish surveying, it's time for your next survey. So hence why you see a lot of variability in the data, but also there is the impression that there's a lot of data there, but because of this rolling survey approach, you kind of have to take that great data with a grain of salt. So that's one of a crazy example. So these are 4 different countries with 4 different challenges of their own, and there is a very pertinent problem of data sparsity, which unfortunately we cannot tackle at this current point in time. So it's basically one of the lessons is how do I extract as much information as I can out of a data set that has limitations on it.
You've got massive spikes in the orange line at the start of every year. Is that because you're smooching out over 12 months?
It's not necessarily a start of every year. So for example, this is actually before.
Whenever there is a big spike. Oh, okay.
Yeah.
Quite exceptional.
I mean, these ones at the end as well.
Well, that's the start.
This one's at the start. This one's in the middle.
Well, the orange line, the orange line's on the blue lines.
Pardon, the orange lines. Yeah. Yes, and there's a very good reason for that, because all we're told is that within this year, I'm allowed to allocate this many.
So, yeah, it's because you've got something you're smooching out with 12 months supply over 12 buckets.
Yes.
And then
The total supply changes in the next year. So that discontinuity is, if the discontinuity wasn't there, I'd be worried. Yes. Cool.
yeah, I'm worried that things that might take some strange data.
Oh, there are a lot of strange things about the data. We can talk about it over drinks later. Now, a preface, I am well aware that there is very high chance of overfitting because the number of parameters has increased. So take everything here with a slight grain of salt of variable size following some distribution of your choosing. But what we have here is the root mean square error of how the net crop predictions fit with the survey data. Now, what I want to note is, if I can go back fast enough, the objective function is not quite root mean square error. It's root mean square error accounting for uncertainty. This one is just root mean square error. One thing that's good for this is that it's good for policymakers because uncertainty bounds are kind of invisible sometimes when it comes to decision making. So it's sometimes useful to put a number on something. And we want to ask, well, is there any benefit in this more complicated, not more complicated, but basically trying to reconcile the differences in the model. On the most part, what we see is, on the left side is if we take the distribution variability into account. On the right side, if we just assume uniform distribution over the 12 months. Generally, we see a reduction in root mean square error where we have more flexibility to fit within the inflated uncertainties of the survey. There's honestly nothing much for me to say here, but okay, there's going to be a lag because, yeah. If we compare, so I recently managed to get hold of the outputs for the previous model that's been rerun to 2024. And if we compare the performance across all countries of the previous model to this one, we see there is a there's a slight improvement in the root mean square error. And generally the variability is larger on the previous model. But again, I want to preface that there is a grain of salt to take in terms of these fits because overfitting is a consideration. But at least now we have a way of getting a bit slightly higher resolution monthly estimates of data. How about the net attrition curves? So those are for two countries. You notice there are two curves because I said there were two types of nets, CITNs, LLINs, that behave quite differently. The thing is, so the surveys tell us whether something is a CITN or an LLIN, and that's where we get these estimates from. And you might ask, why are they sigmoidal? In fact, you had to kind of choose a prior such that they tend to be sigmoidal because of the way nets typically age within these populations from knowledge of the net's dynamics. So we have nice information about net attrition curves. How well does this agree at least to the previous model? Turns out it agrees pretty well. So these are your half-lives for these nets. The blue is the new model, red is the old model. For most countries, it agrees pretty well. Now these odd countries, so the red dots here is because the previous model didn't have values for those. The ones that deviate a lot are typically countries with very dodgy data, or data surveys that were done in very inconvenient or non-useful time periods. So this is done more as a validation to see whether our estimates of net behavior are reasonable. But this part here is, admittedly, was done quite recently and is more interesting than everything I've talked about before, because what happens is you pump nets into a country, more often than not, you're not going to see your access shoot up linearly. It's going to shoot up linearly-ish, and it's probably going to taper off. Now remember that Poisson curve I showed the fit early on. If you were to take that Poisson curve and calculate what the relationship between net access and nets per capita is, in an analytical sense, what you end up getting is something what we expect that kind of grows linearly-ish and then flattens out later on. It saturates. And we actually see this occurring because you can do that to all the countries and find what the linear scaling region is, a la Lyapunov exponent style linear scaling region. And you can take all of that and you can plot, and if you ignore that large uncertainty thing because this is still a work in progress, you can plot how large is that linear scaling region, which means how many nets per capita can I aim for in the country before I stop scaling linearly, and how steep is that scaling. Admittedly, for most of these countries, they actually consist of two linear scaling regions, one where the slope is larger than the other. But from a policy standpoint, this tells you, in a very rough sense, which countries you think would have a larger impact, and for how long does putting more nets in actually increase access in the country? And this is so that's what a model currently stands, but in the grand scheme of things, how does this actually fit into policy and what's happening? So what we have now is more data coming in, which are higher resolution data that's also on a subnational level, so basically within states or provinces. And to add more complication to the mix, now LLINs are not just one type. More LLINs are coming to the market because I mentioned there's insecticide resistance increasingly happening. So basically from 2018 onwards, countries have decided to take in multiple types of nets, of which they probably will all behave slightly differently, which is a problem. And they all vary in efficacy. So the idea is being able to track these net crops by net type would then aid in you calculating how efficacious is your campaign. And on top of that, you also want to figure out what is the demographic of nets in terms of age distribution within the country at any given point in time. And why that's more useful from a modeling perspective is because ideally, what you want to do is make this model, chop it up at a given point in time, keep the net age demographic, and in the future going forward, construct a new model that maybe takes into account the new type of data structures, but you have these net age demographic as an initial condition to feed in, so there is some continuity in there. So that's more the extensibility part of it. And ideally also we want to stop relying on delivery data. So that first component with trying to reconcile delivery and distributions, that was done because we didn't have enough reliable information that we're now starting to get. So this is more like a long-term solution. And I have to black it out because I'm not allowed to show you the data. But essentially we have now, in the worst case, we have like the normal LLINs and we have like 3 other net types. So it gets very annoying to track. And those net curves, they're different countries, but not nicely enough. One improvement of the model is we've just done the infrastructure such that it accounts for multiple net types with their own different curves. Do not take the blue or the green ones, the green uncertainty conditions, as anything useful at all. This is more so the infrastructure itself because there is not enough data to figure out what the net life of these are. But in the future, when data comes in, the idea is that we'll be able to kind of plug this in essentially. But talking about net age, we also have net age. Because we know the attrition curves, we know how things are going in, we can infer what the distribution of net ages are at any given point in time. And these are measured in quarters, which again, as I mentioned before, will be used as initial conditions if we ever want to transition to another model. And you can have stratification by net too. Obviously, these have large uncertainty bars because you don't know the real net attrition parameters for these newer nets. The blue ones are pretty reliable. Red ones, as you can see, are your conventional ITNs, which have slowly gone out of favor because they are not really that efficient. And where is this going to go is essentially we've got the stock and flow, we've got the access nailed down with improvements. Where basically the aim is to take that and plug into the geospatial part, the last compartment, which already exists, and to basically recalculate and get slightly improved estimates of use gap and access gap, which will hopefully inform policymakers a little bit more. And yes, that's 250. That was a lot. Yep. Thanks.
That's a great talk. Got any questions?
Eugene, sorry.
That's okay. We go.
Eugene, has there been work done on mechanistic models with this sort of setup? I know you're concerned with government level things.
Yep.
But but in a sense, you would think that you need to know a little bit more about what happens, say, in local communities. So you tend to expect models where people are using these nets and one family is and the other family isn't, and there's a certain stock of mosquitoes and
Yes.
so what actually happens? Do those mosquitoes decide to go where there aren't nets, and so the net effect is not changed by very much, in terms
Yep.
of malaria. But that's all complicated by the fact that once you get malaria, well, you become, semi-immune for a period. These sorts of things, are there models of that type?
Yes, so Yuval can probably correct me if I get any of this wrong because I'm relatively new, but I believe each of those aspects you mentioned does have dedicated research groups looking at that. So if we're talking about, for example, the studying of actual failure of nets, so the physical failure of nets is one thing. Here we just assume the sigmoid, but there is a mechanism of how these nets tend to fail and how these drugs fail, for example. That has its own separate group that analyzes that part. I believe there is a climate group somewhere talking about the effect of climate and how these mosquitoes might migrate. Yuval probably mentioned once that there is a new breed of mosquitoes coming in that are a bit more resistant, and they're no longer just nocturnal, they're all the time. And yes, all these have been kind of studied in isolation, and one of the challenges is finding a way to marry these bits of findings together, but also in a way that becomes comprehensible and useful for a policymaker.
I know, for example, there's a large group working in Indonesia, in Bandung, ITB, on mechanistic models, but they're really talking about, where mosquitoes breed, where there's a lot of leftover water in pots and that sort of thing, and various techniques for trying to deal with the situation. But they're working more on these mechanistic local models. But you tend to think, that what happens locally is, as I say, the situation in which one family's got nets over them and the next family doesn't is an interesting situation, because the same crop of mosquitoes sort of just find new people to bite, sort of thing. But if there's a slight change in the proportion of what actually happens there, it can be the long-term situation is improved because mosquito populations are going to reduce because of all these factors, and you wonder whether that does make interpreting any data really very difficult.
Oh, yes.
Global.
Yes.
Because you know what the hell the damn will measure.
Yes.
I realise it's very local sort of stuff, but you sort of think that marrying the two, some sort of input of that type would be more detailed information. That might be useful.
Yeah, and that's why we're actually starting to get data on a subnational, so not just national, we're getting survey data on a province level.
Yeah.
So, and the aim would be slowly disaggregating this down to local. Yeah.
And what you described as part of the mechanistic model is open malaria, the one model that was owned by Mr. And you recently moved to medical school, but also the kids does a lot of that in terms of like modeling dynamics with the mosquito, but then also within hosts, like how it develops within the humans. So it's an agent-based model.
Yeah.
That does a lot of that at a particular setting, so at the village level of 10,000 people or anything like that.
Yeah. Sorry. Yeah.
Go back to your expectation maximization page.
Oh. Sorry, it's gonna.
I'm not going to criticize.
No, as in like it's gonna lag because of the figures. It like lags every now and then. Yeah. Yeah, it's frozen.
It's going to take a little while. Okay.
Oh.
We'll get there.
There we go. Got there.
Yeah. So. Oops.
Oh.
Forward. So if I got this right, most of the parameters of these annual monthly distribution ratios in this model, so most of the parameters are being fit in the maximization step. Is that? Have I got that right?
They are being tweaked in the maximization step.
Tweaked.
So they are kept constant when you do the Bayesian regression.
Constant in the expectation.
Yes, exactly.
The place where they're being determined is in your maximization.
Exactly.
And there you are optimizing with respect to that loss function.
Yes,
there.
which is a variation of the deviance information criterion.
So, if you mentioned the possibility for overfitting later on.
Yes.
Most of the risk of overfitting is going to be in this distribution parameter, right? Because there's so many of them. So most of where you have to worry about the overfitting is in this maximization step. Right?
Yes, essentially, and that's why we chose the uncertainty Yeah.
So the uncertainty thing, is that having some sort of a regularization effect for that choice of loss function? Or are you getting regularization from somewhere else?
So the most regularization we have is the fact that, so this log likelihood is calculated with respect to the standard errors, the inflated standard errors with respect to the survey. So it doesn't always have to try to fit it perfectly. So if it has to compromise between two different data points, it won't force it to go between the two if it can. It will try to kind of finalize in between the two uncertainties. So there is that aspect of regularization, but you're right, there's one aspect that I haven't been able to tackle yet, which is typically in this DIC, there is also a penalty term, which is the number of parameters that you're changing. And that would be okay if all the parameters were kind of not so, if that distribution curve wasn't so disjoint in reality. If it was more smooth, then yes, you could say replace it with a smooth function with a limited number of parameters.
Yeah.
But the difficulty is
More like post-stratification or something like that. Is that the right word for it?
bootstrapping.
That's not the right word for it. I'm thinking more we could use some sort of a stratified model for those parameters indeed. So
Yeah.
if you know that campaigns typically happen in May or in this country or something like that, have some sort of model about.
Yeah.
I don't know. You're talking about gradient descent optimization. Are you solving that minimization problem actually to optimality, or are you doing some sort of
No, literally just gradient descent. Gradient descent as in calculate the loss, calculate the gradient.
and then you do that until you actually solve that minimization problem?
We set a number of epochs.
I'm sorry?
We set a number of steps.
So you set a number of steps, so you're not actually fully doing the
No.
minimization.
No.
So you might be expecting some sort of like early stopping sort of regularization there as well, right?
Yes.
Is
So,
that for you reason you've done it that way, or?
so we've done it that way mostly because what we find is that, the first early stopping is basically if it doesn't improve that much anymore, it
Okay.
ends. But also what we find is that after the first two steps or so, the distribution kind of converges and doesn't change too much, even though the loss still decreases a little bit. So we're kind of like trying to,
So you actually think you're getting near optimality anyway?
yeah.
Okay.
And we find that for most cases, those distribution spiky curves stay pretty consistent between each run.
Okay.
Yeah.
Interesting. Okay.
Yeah.
In your comparison of the net retention half-life between your model and Amelia's one, I think yours was consistently
Higher.
higher than Amelia's one. Do you have any reason for why that might be? Is that something from the model?
I think that might be because we're choosing, the choice of model definitely makes a difference. And what you find is, depending on where you choose to have your prior, because the Y-book could have exponential decay as well as a sigmoid. If you choose exponential decay, what you find is that a lot of these sit lower. And I suspect they sit a bit higher for most cases, probably because the actual functional form is different. So there might be a systematic effect on that. Yeah, Amelia's one is basically a sigmoid with truncated ends. And yeah, unfortunately I don't have too much information about her stuff. I could dig through the historical runs. Yeah, but with only one parameter, so it's not as flexible. Yep.
All right. If there's any other really pressing questions, I think we might thank Eugene there. Got any other questions for Eugene? We have to answer those.
I don't know how to.
You say you didn't think you'd be able to take up the full time?
Yeah.
So you're here every Thursday now?
It was way back in the early curve. We had free sharing sessions for treated nets, drugs.
This?
Yeah.
I don't know how to come up with it.
Okay, so you can't explain why does it look like the infected population is actually decreasing even without infection?
No. This.
You ought to give it a
Oh, this. I have no idea.
Because that seems like
I suspect.
like some variation.
Actually, what we find with more interventions, right? They decrease, but immunity actually decreases as well. Because people don't get infected
Let me know.
early enough in patients. It's just it's weird. It's
Right, okay.
if I don't know.
Because I would have thought maybe if this is your behaviour,
Take the fucking off.
I don't know.
Is there any chance that if people say lie or something?
David told me there was.
Yeah,
I
you
would
should put a parameter in your model that tries to capture how truthful the population is, how truthful the sample is.
You know what, this right? Just add a bunch of parameters non-stop, right?
Then what you do is you include a parameter that tries to capture how numeric, like floating point errors, like how much they're taking into account.
Hang on, guys.
Hang on.
Comfortable doing this. There are too many.
Dude, wait till you calculate the gradients on that parameter. It's really fun.
Thanks for answering questions for me.
Do people have a reason to lie about that?
Yeah, I think